Hello again, everyone. So this is the second talk for my topic, I guess. In the first talk, we talked about just some motivation for the problem and gave some key examples of what can go wrong and discussed known regularity results and the theorem we're trying to prove. In this talk, it's going to be more technical, and I wanted to discuss sort of the overall method of the proof without going into too much technical detail, as it would take too much time. So I just wanted to outline the steps and sort of the main ideas as to what how the proof goes. So this talk is about the structure of stable codimension 1 interval varifolds near classical cones of density 5/2, and sort of the setup from the last talk was that we have we work with a stationary integral varifold, which we assume is codimension 1, stable. And by stable, we technically mean its regular part is stable. So we don't worry about the singular set, which by Allard regularity, we know that the regular part is always open and dense, but it could have small measure a priori. And we assume that V has no triple junction singularities. So they were singularities where basically where one tangent cone at the point comprises of 3 half hyperplanes meeting on a common axis, or multiplicity 1. So, and then yes, those are the varifolds we work with, and then we're looking at essentially tangent cones, or just in general cones, C0, which are of the form of a n-1 dimensional axis, and the cross section, the C0 naught, if you will, is a one-dimensional cone in R2, which we're assuming has density 5/2 at the origin, which corresponds exactly to C0 naught having being comprised of 5 half lines through the origin, counted with multiplicity. And then, as before, we had these pictures as sort of representatives of different cases that can happen. Level 0, level 1, level 2, which are the different sort of cross sections that we can have depending on the number of rays that have multiplicity 2. From the stationarity condition, it's very easy to check that the rays in C0 naught have at most multiplicity 2. Can't have anything of multiplicity 3 or more. And then it readily follows that you can only have either 0, 1, or 2 multiplicity 2 rays. So yes, and then the main result we're trying to prove is if we have C0 as above, then there is some epsilon, it depends on C0, such that if V is as above, so codimension 1 stable, no triple junctions, and if we're epsilon close to C0 as varifolds, so in terms of mass and Hausdorff distance, then V is in fact essentially a C1 alpha perturbation of C0, so C1 alpha multivalued graph. And so what we mean by this multivalued graph is we sort of mean multivalued with respect to the multiplicities of C0. So over a multiplicity 2 region of C0, the graph will be a 2-valued graph, and over a multiplicity 1 region, it will be a single-valued graph. So and so sort of the idea of the proof is going to be, as a lot of these regularity results go, is to prove an excess decay statement via a blow-up procedure or linearization procedure, which dates back to De Giorgi in 1961. So recently, this Blob method, it was originally done by De Giorgi, as I said, and then used by Allard and Almgren, and then in 1993, Leon Simon had this sort of seminal paper on cylindrical tangent cones, where he used a Blob method for so-called multiplicity 1 classes, when the cross-section of the cone obeyed some sort of integrability hypothesis. And those ideas have been recently, well, semi-recently in 2014 was when it was finally published in Annals by Nishan, Wickram, and Zekera to sort of a higher multiplicity setting, which is a similar setting we have here. We have higher multiplicity in our cones. So ultimately, the ideas originate the sort of foundational ideas originate from those two works, from the work of Leon Simon in 1993 for the cylindrical tangent cones paper, and from Nishan's work on his stability Codimension 1 stable regularity theory in 2014. So what did I want to say? So yeah, so the proof, we have to work sort of inductively on these different types of cone, these different levels, these cross sections. And this reason will become apparent later, but essentially what the reason for this is that it's possible to have a level 0 cone arbitrarily close to a level 1 cone or a level 2 cone. So if I just quickly draw, color gray, you can imagine that it's possible for, let's say, take a level 1 cone and to split the multiplicity 2 piece into 2 multiplicity 1 pieces nearby, and potentially by perturbing the multiplicity 1 pieces as well, in order to get a level 0 cone, which is still stationary. And by doing this, you can find sequences of level 0 cones that limit onto a level 1 cone. So this means that just because you're close to a level 1 cone doesn't necessarily mean that you are a level 1 cone. You can actually be a level 0 cone. And similarly, level 2 cones, you could be a level 0 cone or a level 1 cone. And so this sort of degeneration property would mean that, well, it means that we have to sort of take these two cases separately. And this is done via, essentially via what's called a fine blob procedure. And the reason where this creeps in is it becomes, if we want to prove regularity properties for the blow-up class of functions that we want to establish. So I will go into more details of this later, but essentially the idea is, for those who are familiar, when we take blow-ups off sequences of cones of this form of the same level, so a sequence of level 1 cones, conversion to a fixed one, we'll get multi-valued functions, or multi-valued harmonic functions, where the number of values depends on the multiplicity in the cone. So for a level 0 cone, we'll end up with single-valued functions because they're all multiplicity 1. And for a level 1 cone, we'll have a 2-valued piece. And of course, the interior regularity, so away from the spine, away from the Rn-1 part of the cone, these are just harmonic functions. And so we have certain regularity results already for them. So we know for the single-valued harmonic functions, they're smooth. 2-valued harmonic functions, we know they're C1/1/2. Again, from work from Leon and Nishan in 2016. However, what we need to prove an excess decay result is we actually need the boundary regularity. We want to know the regularity of these functions at the origin. And so in the single-valued case, provided we have enough estimates to prove some sort of boundary regularity of the boundary values, we can apply standard elliptic PDE theory boundary regularity for single-valued harmonic functions in order to deduce the boundary regularity of functions in the blob class. So the level 0 case is much simpler than the rest because it essentially just boils down to, once you've done similar arguments as to those seen in Leon's cylindrical tangent cones paper, it boils down to just single-valued harmonic function boundary regularity, and everything is fine. However, in the level 1 and level 2 cases, this is no longer the case because we have 2-valued harmonic functions. And there is no known general boundary regularity theory for multi-valued functions, multi-valued harmonic functions in particular. So we can't immediately deduce the boundary regularity for functions in the blob class. And instead, we have to go via a different method, which is, again, it's sort of seen in Nishan's stability paper, which is a reverse Hart-Simon argument. So don't worry if you don't know what this is, I'll write it down later. But essentially, you want to classify the coarse blowups which are homogeneous of degree 1. If you can do that, and provided they lie in a they're suitably nice, you can in fact deduce a C1 alpha boundary regularity theory via sort of Campanato regularity theory. So that linear theory, the so-called linear theory of how you prove C1 alpha regularity for the coarse blob class, is actually included in a separate paper of mine, which was published at the same time as this stable 5/2 paper. And I won't talk about that exactly how that works here. I'll focus instead on sort of the nonlinear theory, the Varifold side of things. Yeah, so once we can deduce, so it boils down to, we want to prove certain abstract properties for the blob class. And if we can do that, we can prove the boundary regularity. And so in this talk, I want to talk about those, how we construct a blob class and how we prove those properties. Okay, so yes, so the idea is the Blob method. And so as a vague outline of the talk, what we're going to talk about is we're going to talk about multiplicity 2 classes. So this is a natural generalization of the multiplicity 1 classes used by Leon in his cylindrical tangent cones paper to this setting. Then we're going to talk about how we construct the coarse blob class using, well, sort of initial L2 estimates. So we're going to find initial graphs and prove initial estimates. Then we're going to talk about density gaps. So this is sort of, if you're familiar with Leon's cylindrical tangent cones paper, the main result there is a dichotomy, which is either we get decay, excess decay, or there's a density gap. And so in this case, we need to deal with that second possibility of density gaps. And we can actually show in this setting, density gaps do not occur, which ultimately is incredibly useful and is what makes this all tick. And then we'll talk about the coarse blob class, how we actually construct them and their properties and the regularity result. And then the final section is in some sense the most technical part, which is one of the properties of the coarse blob class we need to prove is a so-called epsilon regularity property for the coarse blob class. And to do this, this is where we need to worry about that degeneration I talked about earlier. It's where we need to construct fine blobs and something new called an ultra-fine blob. That's what I've called it in the paper. And this is basically to do with the degeneration. Because in the level 1 case, you could have level 0 cones degenerating to a level 1 cone. And in the level 2 case, you could have level 1 cones degenerating into a level 2 cone. But at the same time, you could have level 0 cones that are degenerating to a level 1 cone, which are also degenerating to a level 2 cone. And those rates are sufficiently quick that a sort of a fine blob procedure is not by itself enough to deduce regularity. Okay, so let us begin then. So I'll talk about multiplicity 2 classes first. So I don't want to go into too much detail of this. So multiplicity 2 classes. In my paper, just a second, this is section. So this is section 2.10. So in essence, so a class of stationary integral variables. So we'll call it M sub 2 for multiplicity 2. of stationary integral varifolds is a multiplicity 2 class if it is closed under matrices, rigid motions, so rotations and scaling, and weak limits of multiplicity less than or equal to 2. So again, what this sort of precisely means is that, i.e., elements of M2 are pairs. So we have the varifold part and an open set where the varifold is stationary. So this UV is an open subset of Rn plus 1. V is stationary in UV. And if we have a rotation, an orthogonal rotation of Rn plus 1, any point in UV and scale rho, then we can rotate V and similarly rotate U to remain in the class. And we can rescale homothetically V and also UV remain in the class. So this is the closed under homotheties and rigid motions. And then the weak limit part means that if we ever have a sequence in the class, Vj is a sequence that lies in M2, such that there's an open set which is contained in all the UVJs for all J sufficiently large, and we have finite mass, locally finite mass. Then there's a subsequence that converges to a limit in M2, and moreover, the multiplicity on the regular part is always less than or equal to 2. So under the suitable assumptions, then there exists a VU in M2 such that Vj weakly converges to V in a suitable open set, and the multiplicity of V on the regular part of V is always less than or equal to 2. So we don't get multiplicity more than 2 on the regular parts in the limits. So in particular, we don't have any branch points of multiplicity 3 or more. We have at most multiplicity 2 branch points. So why do we care about working in a multiplicity 2 class? And I should add that the reason we can work in a multiplicity 2 class is essentially, it's the same sort of argument seen in Leon cylindrical tangent cones, is that if we're sufficiently close to one of these cones, we can prove that the density in a sufficiently small neighborhood of 0 is always bounded by 2 plus epsilon for any small epsilon if we're sufficiently close. And then we can use graphical representations away in order to piece things together and show that the multiplicity, we can always assume the multiplicity is less than 2 plus some small epsilon, which isn't enough to know that on the regular part, the density is at most 2. So the reason we want to work with a multiplicity 2 class is primarily just to simplify some of the arguments seen in Nishan stability paper to those seen in Leon cylindrical tangent cones for the graphical representation and the estimates involved. So what we can do is we can prove the sort of a uniform flat regularity result. And so what we mean by this is that there's going to be a uniform degree. We can find a constant such that if an excess is sufficiently small compared to that constant, just that fixed constant on any ball for appropriately rescaled excess for any V, then we have some sort of graphical result. So what I mean by this is we can prove the following. So if you let gamma bigger than 0, and if M2 is a multiplicity 2 class, actually, I'll write this differently. I'll write this in terms of okay, let me set up some notation first, actually. So if we fix for fixed C0 as above, so level 1, 0, level 0, 1, or 2, I is in 1, 0, 2. We define a class of nearby varifolds, nearby, by, so curly n for near, epsilon C0. So here epsilon is just some positive number. So this is the class, of V as above. So Codimension 1 stable and no triple junction singularities, which have we have a mass control. So the mass of V in the open pool is at most 5/2 times the mass of the unit ball plus 1. So this is just some uniform control on the mass to make the mass similar to the cones, because we don't want to have higher multiplicity versions of those cones in our class. And we have a certain closeness condition depending on an excess, and this is now a two-sided excess. So what I mean by this is we have a two-sided excess, V onto C, which is defined via the distance squared of X to C over all of V. So this is the mass of V plus another part, which is over a slightly different ball now. I'll explain what this intuitively is in a second. Now it's the distance from V to C. So here, this radius, I should be using C0 in all of these. So this radius is just the distance from the point X to the spine of C. And the spine is the the linear subspace contained in C. So this will, if X is given by XY in R2 cross Rn minus 1, this will just be the modulus of little x. So we're looking at, intuitively, on one of our cone pictures, we're looking at things, we're taking a ball of radius a half, and we're just making sure we stay away in a sort of stay away from the spine. So we're just looking in sort of an annulus region. So the reason we have to work with a two-sided excess with these two terms is that in theory it's possible for V to be close to C, but C to not be close to V. And that's what we had before with these sort of decomposable cone examples. If you have something which is a sum of a triple junction and a plane, you could have V very close to the plane without being close to the triple junction part itself, if V was just a multiplicity one plane. So that would have small one-sided excess of V onto C, but it would have big excess from C onto V. So we include both parts to ensure that V is close to C and C is close to V. And we work on a slightly smaller ball for C because we want to, in the end, have some sort of interior control. We don't want to be working with the boundary. That becomes clear. It's a technicality that needs to be dealt with. So yes, this is a suitable class of V that we can work with, which gives a good notion of V which are close to C. And indeed, you can prove the result that if for epsilon sufficiently small, if you're in this n sub epsilon of C, then you are actually close as Varifolds to C. And that's a lemma in the paper as well. So the main result then about the multiplicity two classes is that can sort of loosely be stated as the following, that that there is an epsilon, which will depend on the cone, of course, and there's a beta, which again will depend on the cone, such that if we have any V in the neighborhood, the epsilon neighborhood of C, as we're calling it, with, now we're going to have a one-sided excess, so this is a one-sided excess for some affine plane, and that is a hyperplane P. For some hyperplane P, then the conclusion is that over P, locally either V is given by a single valued smooth function or a two-valued C1.5 function. Then V is locally expressible as a C infinity single valued function or C1.5 two valued graph over P. Now the crucial point here is that the beta is completely independent of V. P is independent of everything scale rho, and this enables us to prove certain estimates in a much simpler fashion than that's seen in Nishan's stability paper. And this sort of result is a very simple consequence of the fact, or the definition of multiplicity two classes. So you just had to show that this n epsilon of C is contained within a multiplicity two class. And then once you know that, this follows simply by the results for multiplicity two classes and the fact that they're closed under weak limits of multiplicity at most two using Allard regularity or Nishan's multiplicity two flat regularity results I stated last time. Okay, so that is the sort of the simplification, one of the simplifications we can make in comparison to Nishan's work. So next, I wanted to discuss the course L2 estimates, the initial L2 estimates. So this is when we construct the course block class and we want to prove various estimates. So I want to be conscious of time, so I'll make sure I'm quick. So the idea is that we fix again some C0, stationary level I, and to construct a course block class, we are going to take scaling sequences of suitable graphs that express varifolds close to C0. And so the sort of main initial result for this is the following lemma, that if we fix any tau sufficiently small, tau will give a neighborhood of the spine of C. We don't know we can't express things away from the spine, close to the spine, as graphs, because we don't know what happens when the sheets connect. But away from the spine, we know everything's flat, and so we have either Allard regularity or Nishan stability regularity results to express a single-valued or two-valued graphs. And those graphs are ultimately defined over regions away from the spine of C. And by taking a suitable sequence, we'll be able to take a suitable limit by rescaling them to form the block class. So yes, we take a neighborhood of the spine. Then there is an epsilon, I call it epsilon naught, that depends on C naught and tau, such that for all, if epsilon is at most epsilon naught, and C is a level I cone close to C naught. I haven't been precise by what I mean by this, but I imagine you can guess where I have it's another level 0, a level I cone, so the same level, and it's within epsilon. So I could say it as epsilon close. So we just take the half planes and rotate them a bit. We don't make any stationarity assumption on this C. It's just a nearby cone with the same number of half planes and multiplicities. So it's a level I cone, epsilon close to C, and V is in this curly N of C naught. So again, V is close, so close cone, close V. Then there exists a function U, and I'll write it like this. It's C1 a half over C restricted to the tau complement of the spine. So we look at just everything that's more than tau away from the spine. And by this notation, C, obviously C has multiplicity. I'm meaning a function that has over a multiplicity 2 piece of C is given by a 2-valued function, and over a multiplicity 1 piece is given by a single-valued function. So there's a U such that at every point Z of the form chi eta in the broader radius 3/4 with density of Z of phi at Z to be at least 5 halves, i.e. density of the cone at the origin. Then, so there's the one result that holds without any assumptions, which is just that the varifold V on all of radius 3/4 without this tau neighborhood. I mean tau mod x less than or equal to tau is given by this graph of that function U. So away from the spine, we have some sort of graphical a representation of V. And then we have suitable estimates, which is that the distance from Z to the spine of C. So I guess this is just 0 squared cross Rn minus 1 in our notation. So this is just the spine of C. These all have the same spine. Is less than or equal to C, some constant. Maybe it's best to put a twiddle on it or something to distinguish it from the cones, times the one-sided excess from V to C. And just to recall the one-sided excess, I'll squeeze it in over here. The one-sided excess is the part of just the distance from X to the support of C, dV. So it's that part of the excess, of the two-sided excess. So this tells us that points of density, at least the density of the cone, are close to the spine, with a closeness determined by the excess. We also have a bound on the projections of the unit vectors parallel to the spine on V. Again, the same bound. What this roughly translates to, because of their projections onto approximate tangent spaces, is we have control of the gradient of V, or the curvature of V, in directions parallel to the spine. So in that Rn minus 1 direction. And this will correspond to actually having that when we blow up these functions U, that the derivatives are actually in L2, the derivatives in the direction parallel to the spine are in L2. We don't know anything about the derivatives in the cross-sectional directions, which is one of the problems. Then we have another integral expression, which is the distance squared from X to the support of C, X minus Z. Again, the same bound. Now this corresponds to ultimately it corresponds to a non-concentration result of the excess, that the excess does not concentrate on the spine, provided we have suitable, there are suitably many density Q points, because this only holds at density Q point. So if we know density Q points accumulate on the spine, then this will tell us that in fact the excess, the one-sided excess cannot concentrate on the spine. And this is what actually gives us strong L2 convergence on the whole cone, not just away from the spine, locally away from the spine. We get strong L2 convergence everywhere, which is what we need to pass the limit in these integral expressions to prove things about the Course blood plots. Then we have another bound, which is, again, on things away from the spine. We have that function U minus the orthogonal projection of the X component of the point Z over a suitable sort of control decay, if you will. Decay sufficiently quickly, again, the same bound. And what this actually corresponds to is the function U. We're subtracting just a sort of a constant part. So we're actually going to get control of U minus a constant at every point along the spine, which is in the Campanato world. Campanato regularity theory is kind of like a 0th order approximation of U along the spine of decay, which actually is going to give us C0 alpha regularity up to the spine. And then the final inequality is what's called the Hart-Simon inequality, which was originally used by Hart and Simon in some boundary regularity papers, where we can actually control the derivative, or derivative of u suitably scaled in the radial direction about z. Again, all controllers by the x's. So this is known as the Hart-Simon inequality, or at least some version of it when you take a limit. And where this is used, this is actually used in upgrading the, so inequality V is what gives us the C0 alpha boundary regularity. VI, the Hart-Simon inequality, is ultimately what enables us to classify, well, to prove C1 alpha boundary regularity of elements of the coarse blob class. So these inequalities follow in a similar way to that seen in Leon's cylindrical tangent cones paper, using some ideas from Nishan's stability paper and other results about two-valued functions. So yeah, these very similar inequalities are seen in both of those papers. So what we can now do is, if we argue, when we argue by contradiction in the excess decay result, we apply this with Vk in some epsilon k neighborhood of C, Ck epsilon k close to C naught of the same level, where epsilon k goes to 0 for suitable tau k going to 0, so neighborhoods of the spine. And if we define, that's bad handwriting, Vk, so this is a small Vk now, as the graph, those graphs divided by the excess, we can pass to a limit. Vk in W12 locally, weakly, and strongly in L2 lock, and this is lock away from the spine. Now, the only issue now is that we want to pass to the limit in the inequalities above, which only held when there were density Q points, or at density Q points. So what we want to know now is that density Q, well, density Q, I mean density 5 halves, at least density 5 halves. We want to know that density 5 half points are congregating along the spine. Every point on the spine of C naught is a limit point of density, of points of density at least 5 halves, which roughly corresponds to the symmetries of the cone being seen in the varifold. So how do we do that? This is one of the sort of harder questions to answer in these regularity theorems, is whether or not there are gaps, there are density gaps in the varifolds, which is what those examples I had in the first talk were trying to illustrate that there can be, unless you have some assumptions. And so what we actually have is density gaps we can prove the following lemma. If we have some delta bigger than 0 and C naught as above, then there exists epsilon depending on n, delta and C naught, such that if V is in the epsilon neighborhood as we defined it, then V has no so-called delta density gaps. i.e., for every point in the spine of C, so the translation invariant subspace, not cross, in the unit ball, if we look at the delta ball about Y, the points of density and most 5 halves, this is not equal to 0. So there is some point in density 5 halves involved close by. Okay, so this is discussed in section 2.11 in the paper. And there's actually quite a short, quick proof of this fact using currents. And basically the idea is that if we have the densities less than 5/2, then because we have no triple junctions, the only singular points which can have dimension at most n-1 are actually branch points of multiplicity 2 or classical 2 transverse planes. But from regularity, some work from Leon and Nishan, we actually know that the branch set, multiplicity 2 branch set, is actually codimension 2, so that can't contribute. And so we only have transverse intersections, which again from Nishan's regularity theory, we know are actually immersed points. So this we can actually define currents which have no boundary in a density gap region. And if this were to fail, we could find a sequence of epsilon going to 0 with currents of no boundary and pass to the limit, which would then get a current of no boundary. But these cones with 5/2 do actually have a boundary. So we'd get a contradiction. Okay, so with the fact that there's no density gaps, what this implies is that all those estimates from above actually hold along the spine, and so we can actually pass to the limit and get that these hold along the spine. And in particular, we get strong L2 convergence away, as I sort of mentioned above. So now that enables us to define the blow-up class, which is just all those limits as above when we take those sequences of graphical representations and blow them up. So that leads us to the coarse blow-up class, where so the coarse blow-up class, which we denote, so the coarse blow-up class, which is curly B of C naught, is the class of all functions V constructed above, as constructed above. And you can prove all sorts of properties for this coarse blow-up class. So we know each element is in L2 up to the boundary of on each half hyperplane, valued orthogonally on each half hyperplane. We know it's in L2 lock away from the half hyperplanes. So you may as well rotate everything, so it's defined on one half hyperplane. We know that, again, from sort of the minimal surface equation, that they're actually harmonic in the interior, because the minimal surface equation linearizes to the Laplacian. We have suitable boundary estimates given via these two inequalities and the Haas-Simon inequality. Not the first one. Yes, the first one gives the L2 strong convergence, and then we have these sort of boundary results for decay at the boundary. And we have certain closure properties. We can rotate these things because we can just rotate the sequences of Varifolds, and we can actually, so we can subtract off the sort of linear part of the average as well via, again, a suitable rotation argument. And again, we have a suitable actually compactness property as well, again, from compactness results of Varifolds. So all of these properties are listed in the paper in section 4, but the hardest one, or the most non-trivial one at least in this setting, is the sort of so-called B7 property, which is also an epsilon regularity property. And without being too specific for time reasons, because I think I'm going on for a while now, what this roughly says, if we have an element, so if C naught is level I and V is in the blob class of C naught, is close to a level less than I cone. And by this, I mean the graph of V. So the graph of V is defined over half hyperplanes in C0. And so if the graph of V actually is close to a level I cone, so the multiplicity two pieces split to two approximately linear pieces, then in fact, V is C1 alpha up to the boundary over each half hyperplane in C. So what this sort of means is that, yeah, if we're close to a level, so if we blow up of a level 1 cone, if a blow up is actually close to a level 0 cone, then it is actually C1 alpha up to the boundary. And sort of the thought process should be that if you take such a blow up of a level 1 cone, which is close to level 0 cone, if you translate this back to what this means for the sequence of varifolds, it actually means that the varifolds are decaying to a level 1 cone, but they're actually much, much closer to level 0 cones. And under that assumption, you want to actually prove that the varifolds are actually perturbations of those level 0 cones as opposed to level 1 at the level 1 cone. And the thing is, in the level 0 setting, this epsilon regularity property trivially follows because you can't decompose into more cones than more half planes than 5. And as I said before, it just results from harmonic function regularity. So we can actually prove directly from the other properties of the blow-up class that the elements of the blow-up class are C1 alpha up to the boundary. And then we use that to get the excess decay. For the levels 1 cones, we want to use the fact that we understand the level 0 cones, and in fact we have the regularity theorem there, to prove this epsilon regularity property for the level 1 blow-up class. And then that involves a so-called fine blow-up procedure, as similarly seen in Nishan's stability paper. Except now we're doing a fine blow-ups off of non-flat cones, which it's only technical changes to the argument, essentially. The main difference now is that when we actually take the fine blow-up class, in the level 2 case, we could have, as I said earlier, level 1 cones degenerating, but also level 0 cones degenerating to those level 1 cones, which are in turn degenerating to level 2 cones. And that involves, then that could result in actually still being a 2-valued piece in the fine blow-up class, for which we still don't have boundary regularity theory. So to get over that, you have to do an even finer blow-up procedure called an ultra-fine blow-up procedure to establish the boundary regularity for the fine blow-up class, which in turn can be used to prove